motion of reduced mass under inverse square force. Okay, motion of reduced mass under inverse square force. Okay, chapter motion of reduced mass under inverse square force. Okay, motion of reduced mass under inverse square force. Okay, the most familiar example of inverse square force is the gravitational force. For forces gravitational attraction between the two mass points m1 and m2, F r vector equal to minus g m1 m2 upon r square unit vector r. Okay, r mu d square vector r upon dt square equal to mu double derivative of r equal to minus g m1 m2 unit vector r upon r square. Okay, r m1 m2 upon m1 plus m2 double derivative of r vector equal to minus g m1 m2 unit vector r upon r square. But double derivative of r equal to minus g capital M upon r square unit vector r, where capital M equal to m1 plus m2. Okay, this is clearly the equation of motion of a particle of unit mass at a vector distance r. 1 minute. This is r1 vector and this is r2 vector, m2 m1. Okay, this is clearly that the equation of motion of a particle of unit mass at a vector distance r equal to the distance between the two particles from a fixed mass capital M equal to m1 plus m2, capital M equal to m1 plus m2, exerting a force of attraction and it further the acceleration of one mass with respect to the other mass will appear to be the same but in opposite direction. Okay, either the observer is at mass m1 or m2. Motion in the center of frame. Motion in center of mass frame. Okay, mass frame. In the absence of any external force acting on the system, its total linear momentum is conserved. Okay, hence the velocity of center of mass remains constant in an inertial frame. However, in the center of mass frame, the velocity of center of mass is 0. Okay, the two particles or bodies move around the center of mass in such a way that the vector distance vector r between them remains constant. Okay, hence to an observer at the center of mass, the heavier mass seems to describe a circle with a smaller radius and the lighter mass seems to describe a circle with the larger radius. Okay, then circle with the smaller radius and the lighter mass seems to describe a circle with the largest radius because R2 upon R1 equal to minus M1 upon M2. Okay? R2 upon R1 equal to minus M1 upon M2. Okay? Thank you. Next study, center of mass and reduced mass of two particles. Center of mass and reduced mass of two particles. Okay? Center of mass and reduced mass of two particles. Okay? For two particles are mass point M1 and M2 laying at a vector distance R1 and R2 from the origin. The position vector of center is given by. Okay? For two particles are mass point M1 and M2. Mass point M1 and M2 lie at vector distance R1 vector and R2 vector. R1 vector and R2 vector from the origin. From the origin. Okay? From the origin. The position vector are the position vector are of center of mass is given by vector R equal to M1 R1 vector plus M2 R2 vector upon M1 plus M2 in previous. Okay? The center of mass of two particles lies on the line joining the two particles. The center of mass of two particles the center of mass of two particles lies on the line joining the two particles. Joining the two particles. Okay? Two particles. Okay? When the center of mass lies at the origin, if the center of mass lies at the origin, then vector R equal to 0 and M1 R1 vector plus M2 R2 vector equal to 0 or M1 upon M2 equal to minus R2 vector upon R1 vector minus R2 vector upon R1 vector. Okay? Thus the center of mass is the center of mass is a point which divides the line joining divides the line joining the two particles, joining the two particles in the inverse ratio of masses. In the inverse ratio of masses. Okay? Thus the center of mass is a point which divides the line joining the two particles in the inverse ratio of masses. Okay? Reduced mass. Next is reduced mass. Reduced mass. Reduced mass. Okay? When there is no external force acting on the system of two particles and the only forces are those of mutual interaction, then the system behaves as a single particle of mass. Okay? Then mu equal to m1 m2 upon m1 plus m2. m1 m2 upon m1 plus m2, because when there is no external force, reduced mass, when there is no external force acting on the system of two particles and the only forces are those of mutual interaction, then the system behaves as a single particle of mass. So mu equal to m1 m2 upon m1 plus m2. Okay? In such a case, mu is known as reduced mass. In such a case, mu is known as reduced mass. Reduced mass. Okay, of the system. It acts at mu acts at point known as center of mass. Acts at point known as center of mass. Known as center of mass, which divides the line joining, which divides the line joining the two particles line joining the two particles in the inverse ratio of masses. In the inverse ratio of masses. Okay? Mu reduced mass. Okay? Mu acts at a point known as center of mass, which divides the line joining the two particles in the inverse ratio of masses. Okay? Importance in physics. Reduced mass. Importance in physics of reduced mass. Okay? Next is importance in physics of reduced mass. Okay? 1 minute. Importance in physics. Importance in physics. Importance in physics. Okay? Importance in physics. 1 minute. Okay? The first point. Okay? The importance of center of mass and reduced mass lies in the fact that instead of having two separate equations of motion. Okay? The importance of center of mass. The importance of center of mass and reduced importance of center of mass and reduced mass lies in the fact that instead of having two separate equation of motion. Okay? Equation of motion. So m1 and double derivative of r1 vector equal to f12. Force acting on force acting on one particle by another particle, okay? And equal to function of r vector, unit vector r, and m2 double derivative of r2 vector equal to f21 vector equal to minus f vector, function of r, unit vector r vector, okay? We have a single equation of motion involving reduced mass mu is given by, but mu double derivative of r vector equal to function of r, unit vector r, where vector r equal to r1 minus r2 vector, r1 minus r2 vector, thereby reducing the two body problems through one body problems, okay? Thereby reducing the two body problem to one body problem, okay? One body problem. And the second point, okay? When the center of mass is taken as the origin of the coordinate system, when the center of mass is taken as the origin of the coordinates, system, then capital R equal to 0, the velocity of center of mass, the velocity of center of mass V equal to derivative of R equal to d derivative of R upon dt, okay? d upon dt, vector R equal to 0, and linear momentum vector T equal to mu v vector, okay? As the system is also 0, so mu being the reduced mass, okay? This fact is made use in having a center of mass. This fact is made use of in having a center of mass, frame of reference for the study of collision phenomenon between particles, okay? Second point, when the center of mass is taken as the origin of the coordinate system, so capital vector R equal to 0, the velocity of center of mass is v vector R equal to dr by dt equal to 0, and linear momentum P equal to mu v equal to 0, okay? Mu is being the reduced mass. This fact is made use of in having a center of mass, frame of reference for the study of collision phenomena between particles, okay? Thank you. Next study is interacting two body system reduced to one body problem. Okay, thank you.